Okay, so this is take three, so it's going to be pretty quick, hopefully. Basically, the scenario is you have a bullet that's being shot into a block that it has a mass of one, and we know that if it is fixed using a vise, it travels a distance of 8 centimeters into the wooden block. And if otherwise, we reuse that same block and shoot a second bullet into it without it being fixed, we know that it likely moves because it's a frictionless thing, and if you shot something into something that could glide over things, it would probably move. We also know that it is also going to be embedded, and we're asked to find out how much of a distance it gets embedded. And the question really revolves around understanding what kinds of things are conserved. And so far we've covered conservation of energy and conservation of momentum. And the clues to sort of pick apart a problem like this is the fact that there is some distance factor being calculated. There is something that is transitioning from being fixed to being frictionless, and as a result it's likely to be moving. And we're also told something about the mass of the block. So we kind of figured that the mass of everything is going to play into the problem. And so I'm going to sort of lay it out so that we can um, write it in terms of conservation of energy and conservation of momentum. So I'm going to back in the day we visited the idea of conservation of energy, and we said that any net amount of work is going to be equal to the change in kinetic energy and the change in potential energy. And that when work is zero, something happens. I'll leave you to answer that. But it's, that's one scenario. And the other is conservation of momentum, in which case the mass and the velocity of a particular system it should be conserved in a final state and an initial state. Cool. So if we were to take a look at this particular problem in terms of both of them, right, we would have to write out conservation of momentum and conservation of energy. And looking at this particular drawing right here, we're going to say in scenario 1, is there conservation of momentum? Or can we use it to our benefit? And if it doesn't, it should come to you pretty naturally that we can't necessarily use conservation of momentum. And the reason behind that is because the mass itself is fixed, which means there isn't actually any velocity at the end, so that when we were to use conservation of momentum, we'd have a 0 or 1 end. And it doesn't particularly help us. We could pursue that path, and I would strongly encourage sort of going down that path. But if you don't have the time, just consider the fact that a system involves a single bullet at the very beginning and involves a bullet plus a variety of other things which aren't moving at the end, right? And so the only comparison between the beginning and the end is the bullet movement and the bullet stopping, and you really can't derive a lot of information out of that. So we'll strike out conservation of momentum from that. We can't particularly use it. We can use it, but it wouldn't be particularly useful. Conservation of energy. Well, let's see. Can we say anything about the fact that is there some energy transfer all happening? Well, there is, because there is a certain amount of work that was done to stop the bullet from moving when it was, after it had been moving at some velocity. The block was doing some sort of blocking, right? And the bullet was being prevented from moving any further, and it was only able to embed itself for 8 centimeters. So let's just go down that path. So we'll rewrite our conservation of energy equation, 1/2 mv f squared minus 1/2 mv initial squared, plus but I'm going to make this case that there is no potential energy. The reason being there's nothing going down or going up, right? So there's no change in, there's no effect of gravity. So this is going to be equal to work. And that amount of work is what is done by the bullet to lodge itself to a certain amount of distance. So whenever we say by the bullet, it's also important to keep in mind that work is always going to be done by a system on a system, and therefore it's also complementary to consider the work done on the bullet by the block. So if we so we're going to say, what is work? Well, work is nice as a big fat W, but we can also define that as force times distance. Aha. So let's see, are there any particular things we can derive or can we substitute into this? And this is going to be one of those problems where we can actually benefit from not immediately substituting values in, but reusing them as we go along. So unfortunately, I think that's not going to show up, so I'm going to rewrite underneath right here. What is V final? What do each of these represent? Well, V final represents the velocity of the block plus the bullet. Remember, we're looking at this from this particular scenario's point of view, so we can, even though we're going to use this nomenclature and we're going to reuse it further along, we know immediately that this is going to be 0. What is V initial? V initial is the velocity of the bullet itself. Right? We don't know anything about it. We do know the mass, and we know that the amount of work translated to it being embedded a certain distance. So that's going to be distance. So that's equation number 1. Let's rewrite it. So 0 minus 1/2 mass of the bullet V of the bullet equals force times 0.08. Great. That's one equation. Scenario 2. Can we use conservation of momentum? Well, things are moving after the impact happens, so I'm going to make the argument that we can. So we're going to use that mv final equals mv initial. And once again, that v final is going to be the velocity of the block in the bullet. We don't know what that is, because it could be moving at a certain distance, at a certain speed. We know what that is. Do we know what mass of the final system is? It's going to be actually 1.014 kilograms. The reason being, we have 2 bullets and the mass of the block. Right, so 7 grams plus 7 grams plus 1 kilogram. V final equals, what is the mass of the initial before it hits the block? It's going to be 0.007 V initial. Cool. So that's equation numero 2. And equation number 3 is going to consider conservation of energy. And once again, we can actually make the case that conservation of energy is at play here, because the amount of velocity that the bullet is traveling at gets translated to it being stopped by the block, and that amount of force or energy required to move the bullet is then being translated to a movement of the block and the 2 bullets itself. So that ends up being, once again, 1/2 mvf squared minus 1/2 mvi squared equals f delta x. Now this delta x is what we're looking at. We're curious as to what is the distance of the bullet being lodged into the block for the second time around. We know what the mass of the entire system is at the end, 1.014 v final squared minus 1/2 m, so 0.007 v initial squared equals f delta x, where delta x is what we want. Awesome, so that's equation numero 3. Now, you'll look at this and say, okay, well, you've got to do one other equation, don't you? Because you have one unknown, two unknowns, three unknowns, four unknowns, and you just have three equations. So that would be the case, except there's actually a really clever insight that comes out of this and might be helpful to consider in future exams and quizzes and the like. It's the fact that all of these equations potentially can share something in common. Right, so if we make sure that we, if we look at this one, I didn't. Let me try to use a different colored pen. But if we look at our equations here, right, 1, 2, and 3, there's a little trick. Notice that there is this actual element right here is used right here, which means that there is actually the potential that we never have to actually consider v initial or what its meaning is, because all we have to do is solve for this particular thing as one unit and then plug it back into the system. So if it doesn't make any sense right now, follow, just let's hang on for a bit, and hopefully it'll make sense a little more further. Awesome. So let's first solve for VF right here. VF is equal to 0.007 V initial divided by 1.014. Awesome. So this is taken care of. Now, what we're going to do is then we're going to stuff that into here. So we have 1/2 1.014 times times VF, which is 0.007 over 1.014 V initial squared minus 1/2 of that. And if we were to consider this as one variable, then we have two equations, and if we're going to be solving for this, two unknowns. And that's the neat trick about this. So let's try to bring this particular element outside so that we can factor it out and actually potentially substitute this in. So I'm going to say, let's bring out 1/2 0.007 V initial squared. That's our big factor right here. And we need to convert this into into its equivalent here. And I'm going to just do a real quick calculation right here. It's going to be 0.007 squared over 1.014 squared. That's the inside of this, right? Because you're squaring that. Multiplied by 1.014. So that becomes this. And we want to translate this into let me just say, so what we have right now is 0.007 VI squared, and we want to translate that to this, because this is what we have right here, right? So actually it's 1/2, but we can get rid of that factor. So I'm going to say that if we were to multiply by 0.007 and divide by 1.014, right? If we were to multiply these two together, then we would have this. Right? So if we do the exact same thing, if we were to multiply this multiplied by 0.007 over 1.014, we would actually get that. So just to do a real quick calculation in your head, this would be 0.07 squared over 1.014, and if you factor this out, that's exactly what you get. Cool. Minus, and so we have to do the exact minus 1. Right, because we've pulled this out as a factor, equals f delta x. Cool. So this is mega equation number 1, and mega equation number 2 happens to be the one last equation that we haven't used, which is this one. And lo and behold, if we solve for 1/2 0.007 vi squared equals negative f times 0.08, right? Because I just switched the negative sign. Then we can bring this into here and say negative f times 0.008, right? Multiplied by, and I'm actually going to calculate that right now if I can get my calculator. It should be something along the lines of yep, so 0.0069 minus 1, so that becomes, this becomes 0. I hope you can see, yeah, 0.993 negative equals, just finishing my train of thought, f delta x. And so that multiplied by 0.008 negative f equals f delta x. Just to be very explicit, we want to find delta x. Looky, we can take out the positive sign. We can also take out the f and solve for delta x is equal to 0.008 times 0.993 is 0.00, sorry, that's times, so that becomes 0.00794 meters, or 1,000 meters, 1,000 centimeters in a meter, so 7.94 centimeters.